Hello everyone. Today in this section 2.4 I'm gonna give you guys a precise definition of the limit. Alright, and this is credited to a mathematician named Cauchy. It's used in something called the epsilon delta definition. I bet to many of you guys this is a very new language. It's kind of difficult to get at first. So let me walk you guys step by step slowly to get to the definition. And by the way, when we move on to the upper level of mathematics, we kind of use less of our intuition and we kind of base on definition instead. So definition is the most important thing in mathematics, in my opinion. So we have to go through this carefully. Make sure that you understand it precisely. Of course, when we move on to a higher level, we're going to have more general definition of limit, but for calculus level, the epsilon delta definition works just fine, so we go over it. Let's recall the definition of limit, the idea of it, Okay, say we have a function, f of x, okay? Doesn't matter if it has a missing point, let's say a point A right here, and this is L. We say that the limit of f of x when x approaches a equal to L, and what we really mean is when we have any input x getting closer to the value a, this is a again, not 9, a. At x getting close to a either from the left hand side or the right hand side, then the output f of x gonna getting closer to the value L. Okay? X getting close to A, and f of x getting close to L. This is the arrow that I'm trying to draw. Okay? Close to L. That was the point. In other words, any point on the graph, when you move along x close to A, and that point on the graph will get closer to this point right here. That was the idea. Question is, how can we translate that idea into a mathematical language that's correct all the time in terms of real numbers? And here's the idea. I'm going to go step by step. All right. So what we're trying to say is that if x getting close to A, then f of x is getting close to L. Again, I'm trying to walk you guys step by step to the formal definition. So this is the idea. See, with the value of x is close to A. I never say that x equals to A. Okay, I say that I'm saying that x is getting close to A in terms of real numbers. The value of f of x is gonna be close to L, and that is what we're trying to say. The limit of the function f of x approaches L when x approaches A. Okay. All right, and what do we mean by x getting close to A? It means that the distance from x to A, let me write distance this way, is that okay with you? X minus A in absolute value means that the distance between x and A is small, then the distance from f of x to L is also small. Okay? X close to A, then f of x close to L. Okay? So small. Then this one is small as well. And we, instead of writing small, we denote that small value by delta. Delta, by the way, delta. Okay, so we write this way. If x minus A is pretty small, smaller than a small number, right? Say, if this is 5, this is what? 5.1, 5.01, so the distance between 5.1 to 5 is 0.1, right? This is the delta we're talking about. This is small. Then f of x minus L is going to be less than some smaller number, epsilon. That's what? Called epsilon. You see that the rate, the speed of x moving toward A may be different from the speed that f of x goes to L. Okay, see, so longer distance here, shorter distance. It depends on the slope of the graph. Right? So all we're trying to say is what? When x is getting close to a value, then the function is getting close to another value. Instead of writing things in English, we try to use math notation. Of course, then right here can be displayed by this arrow. If this, then that. Conditional statement. Okay. That was the main idea. You see the notation of delta and epsilon coming up. Okay. Now let me turn the definition around a little, explain more before I give you a full definition of it. I want you guys to think of the limit from right here as like an approximation. Okay. And again, keep in mind that we are focused on concentrate on this statement right here. X getting close to A, then f of x getting close to L. Say, make it easy. Example, say A equal to 5 and L equal to 7. So x close to 5 and f of x close to 7. All right, I'll stick with this. So think of approximation. Say I want to approximate the L with x is close to 5. What is f of x equal to when x is approximately equal to 5? You see the way I'm writing it is not exactly equal to 5, okay? Getting close to 5, okay? What is f of x equal to? Of course, you can guess in this example right here, this is f of x going to be approximately equal to L when x is approximately equal to 5. Okay? It's another way of saying it's pretty much the same. X close to 5, f of x close to L, or 7 in here. 7 in the example. Okay. Or I can write A and L in general if you like to. Just 7 and 5 I think is a little bit easier for you guys to think. And then later on you can replace letter A by, number 5 by letter A, and then number 7 right here by letter L, and this give you a definition. Okay. So what f of x equal to? When x is close to 5. That was the main question. Okay, and you said that I want my approximation is within 0.01 of error. Okay, when x is close to 5, I want to approximate f of x within that much of error. So in statistics, it's called margin of error, or margin of error. Okay, and in this particular example, if you say 0.01 as a margin of error for f of x, that means that the epsilon is about 0.01. Means what? When x is close to 5, then f of x is somewhere between 6.99 up to 7.01. You see, I still don't know the exact value of f of x, but I know that when x is close to 5, f of x is around there. That was the idea. So say one more time. We try to approximate the value of the limit L. In this particular example, 7. When x is approaches 5, okay? When x is close to 5, what would be the output when x is close to 5? And in terms of statistics, we talk about margin of error. Say what? I want to approximate the value of the function when x is close to 5 with the errors of around 0.01. And let me try to rewrite this a little bit clearer, make it easier for you to understand. Okay, this line right here, I can write it one more line equivalent to this. This is no more than this. X is somewhere between A minus delta to A plus delta. And this is the same thing as writing f of x is somewhere between L minus epsilon to L plus epsilon. And you guys are going to see it clearer from here. And this means this. When x is about delta away from value A, so this is delta that we're talking about. Then f of x is about epsilon away from the limit. See? F of x is between L plus or minus delta. Okay? See? And this one right here, x is between what? A plus or minus delta away. Okay. So the formal definition say this. If I want to approximate the limit L within the epsilon error, so given any epsilon positive, and keep in mind, think of it this way, this is like the margin of error. Okay? Doesn't matter how small the error gonna be, or how big the error gonna be. You want to approximate the limit L within epsilon error. We can always find the error for the input x. There exists a number delta positive such that if x minus a absolute value less than delta, then f of x minus L absolute value less than epsilon. Okay, and this is a pretty formal definition of limit using epsilon delta language from Cauchy, pretty long time ago. So pretty much the definition says this: if I want to approximate the limit within the error of epsilon, that much of error, then I can always project it down to the x-axis, and I can find the interval where x falling in there. For sure, the error for the limit L going to be falling to epsilon. And since the error for x and the error for f of x is different, we use two different letters. Delta is for x and then epsilon for f of x. Okay, and this is the definition. And you see some English in here. A more formal way of writing this, I'm going to use all math notation just in case as you guys are interested in. This notation means for all, okay? For any epsilon positive, I can always find there exists a number delta positive such that if x minus a is less than delta, and for sure I will have f of x minus L is less than epsilon. And this is the formal definition of Cauchy using epsilon delta language. To make it easier for you, let me try to give you an example, break it down step by step, and you guys will see the idea of it. X in here, f of x in here. I have a function right now, I don't know what it is. My function f of x, okay? And this is my point right here. Say this is 5. Say this is 3. Say this is 2.7, and this is 4.5. This is 3.3, and this is 5.4. Okay. So if I show you the graph right here, you see when x is approaching 5, f of x is approaching 3. Is that right? And actually, that's actually right. But now I'll talk about in terms of the definition of limit that we just learned. Okay. I want to approximate f of x. F of x is approaching how much when x is approaching 5? Okay, the question, f of x approaching how much when x is approaching 5? And I'm giving you the margin of error, epsilon, is equal to 0.3. We good? You see that in here, x equal to 5, f of x equal to 3, right? So we can calculate the two boundary right here. See what happened? 0.3 for epsilon means that from 3 is the middle, you can go down 0.3, you can go up 0.3. Okay? And then from that boundary, from this interval right here, for f of x, you can find the interval for x. So when 3, you go down by 0.3, you have 2.7. You calculate, and here I actually give you already. When f of x is 2.7, x is 4.5. When f of x is 3.3, x is 5.4. That's, you know, this is 4.5, this is 5.4. So you know that when x is somewhere between 4.5 all the way to 5.4, then for sure f of x is going to be somewhere between 2.7 and 3.3. Okay? And this one is for epsilon is equal to 0.3. Question, can you calculate delta? What is delta? Such that f of x is somewhere between 2.7 and 3.3. Okay? So how do you find delta in here? You see that we don't have the same distance from 5. 4.5 to 5 is 0.5. 5.4 to 5 is just 0.4. We had to choose a bigger value between the two. So we had to choose delta is equal to 0.5. Why is it? When delta is 0.5, then x could be anything from 4.5 to 5.5. Any value any value of x between 0. I'm sorry. Was that right? And the epsilon right here. And sorry, we have to choose a smaller one. I was wrong. We choose delta is 0.4. 0.5 is going to be out of, you see right here, it's going to be out of the interval. We have to choose a smaller one, 0.4. So given epsilon between 2.7 to 3.3 means epsilon is 0.3. We're going to calculate the lower bound for x, the upper bound for x value, and then we choose the smaller distance to the value of x. So this is 0.5, this is 0.4. We better choose 0.4. Because when I choose delta equal to 0.4, the actual interval for x is going to be from, let me use red color, from 0.6 up to 5.4, because we only choose the smaller one. This is 0.4, this is 0.4 away, and we plug in any value of x between 4.6 all the way to 5.4, and we're going to have the output f of x somewhere between this point right here all the way to 3.3, and that will satisfy the condition. Okay, so in this particular problem, example, not the problem, we want to approximate value of f of x when x approaches 5 with the error of 0.3. The answer is this. Given epsilon equal to 0.3, we find delta equal to 0.4 according to the graph. Okay. Again, 5 is in the middle. We try the distance to the left is 0.5, right is 0.4. We have to choose a smaller one, right? I make a mistake at the beginning and say the bigger one. No, not right. Smaller one. Find delta equal to 0.4. We find delta equal to 0.4. Such that when x is between 0.6 to 4.6, I mean 4.6 to 5.4, of course 4.6 to 5.4 is included inside 4.5 to 5.4, so our interval is safe. It's really contained inside the big interval. When x is between 4.6 to 5.4, then for sure when x is between this less than 5.4, when x is between 4.6 to 5.4, then for sure f of x gonna be somewhere between 2.7 to 3.3. Okay, and they satisfy the condition that epsilon is 0.3. That was the idea. How about one more example? Make sure that it's clearer, because this is a big concept. So it's a little bit complicated. Try one more. Same idea, just repeat the same thing one more time. I use the example in the book. Okay. X here, y here. This is my function. This is 2. This is 3. And this is 3.2. This is 2.8. This is 2.9. 2.3, and this is 1.5. And 0 right here. Okay? They're trying to tell you what? The limit with x getting closer to, then f of x is getting closer to 3. Okay. Now in terms of epsilon delta, when f of x is close, we need f of x is close to 3 with the errors of 0.2. So you see from here you can calculate epsilon is equal to 0.2. 3.2 minus 2, or 3 minus 2.8 is 0.2. 3 plus or minus 0.2. That's how you have the interval right there. Okay? Question is, what value of x can you plug in to guarantee that f of x is somewhere between 2.8 to 3.2? What value of x, one more time, can you plug in so that the output f of x gonna for sure will be between 2.8 to 3.2? Of course, looking at the graph, and you're gonna have what? 1.5 less than x, less 0.2.3, then for sure f of x gonna be somewhere between 2.8 to 3.2. See, you plug in any value from 1.5 to 2.3, you're gonna get something else somewhere between 2.8 to 3.2. But the thing in here is what? 1.5 and 2.3, number 2 is not right in the middle. So we have to choose an interval for sure at work. We're looking for the smaller distance between those two. This is 0.5, right? I think 2 minus 1.5. And this is 0.3, right? This work, and I'm going to say something that let's make it look like interval around x, even though it's not general like this. And then if this works, then what? I'm going to choose delta is equal to 0.3 in here because I choose smaller one. So 2.3 is going to be the upper bound. But the lower bound, I'm going to choose 1.7. So this work, and this one will work. If any x between 1.5 to 2.3, then f of x is going to be between 2.8 to 3.2. Then for sure, that any x between 1.7 to 2.3, that thing going to be happening as well, because this interval is contained inside that interval. And what is so good about this? And you have now that x is right in the middle, right? The 2 is right in the middle of 1.7 and 2.3. So we're going to choose delta equal to 0.3. And the definition is going to match, say what? If you are given epsilon equal to 0.2, again, epsilon here means what? If you allow me to get the error of 0.2 around the limit point. So I have the interval somewhere from 2.8 to 3.2 for f of x. Then I can find, find the value delta equal to 0.3. Right here, I can find delta equal to 0.3 such that if 1.7 less than x, less than 2.3, this is another way of saying that x minus 2 is less than 0.3, right? 2 minus 0.3 and 2 plus 0.3. Same thing. Then f of x is somewhere between 2.8 all the way to 3.2. And this is another way of saying that f of x minus 3 is less than 0.2. All right? Now, I'm going to give you another example, which is the hardest part of the type of exercise of this section that you may see in your homework. Use the definition of the limit to calculate the limit, to prove that the limit is right. I'll show you an example. And look at the exercise in the book. Okay. Show that limit of 2 plus 4x over 3, 2 plus 4x over 3, when x approaches 1 is equal to 2. Actually, this is a line, right? When x approaches 1, then that function right here is the line gonna get to 2. And let me sketch a graph for you to see it. Okay, the line gonna be like this. Okay, it's 2 right here, x right here. I'm sorry, 1 right here, x is approaches 1, f of x approaches 2. What's the idea? It's easy to prove if you know the formula before. To plug in x equal to 1 to simply x equal to 1, then what? 2 plus 4 times 1, which is 4, 2 plus 4 is 6, divided by 2, 3 is equal to 2. But that formula really comes from the definition of limit that we're about to show right here. Limit is always, definition is always the hardest thing. Proving anything using definition is always the hardest thing. Okay, let's go through this. So, first of all, given any epsilon greater than 0, okay, small, I mean, greater than 0. So, I want to have epsilon in here, a little bit more than 2, a little bit less than 2 right here, right? And I want to find delta equal to something such that if x minus 1, say my a right here is 1, okay? So x minus a is, in this case, x minus 1 less than delta, then I will get a function which is 2 plus 4x over 3 minus a limit which is 2, okay, the limit L equal to 2. It's less than epsilon. This is L. Okay. Now that work with x close to a and f of x close to L. We're gonna prove that limit equal to 2 using the limit definition. And the definition say what? Whenever you are given an epsilon positive, your job is to find delta positive. Okay? Whatever epsilon they give you right here. Doesn't matter how big or how small that epsilon they give you, you can always find the value of delta. This is delta. Okay? You gotta find delta. And it's not specific number anymore, just a random letters, and you can always find delta. Satisfy the condition as if x is delta away from number 1, x minus 1 to delta, then for sure f of x is going to be epsilon away from the limit 2. Okay, so the strategy for proving this problem is to go backward. We start from here. Okay, let's simplify this. Say if you have epsilon given already, you have 2 plus 4x minus 2 over 3 less than epsilon. I'm going to simplify this. I got what? 2 plus 4x over 3 all the time, okay? Keep that in mind whenever you use definition. You go backward from the result, back to delta. Minus 2 is minus 6 over 2. This is 2 plus 4x minus 6. I'm sorry, over 3, right? 6 over 3 is over 3. This is 4x minus 4 over 3. I simplify, combine the like terms in here, and I factor out the 4. I got 4 times x minus 1 over 3. Okay, so this one is the same thing as 4 over 3 x minus 1. Absolute value is less than epsilon. We just simplify, and 4 over 3 is a constant. We can pull it down. 4 over 3. Absolute value of x minus 1 to be less than epsilon. In other words, x minus 1 going to be less than 3 over 4 epsilon. I multiply both sides by the reciprocal of 4 over 3. I got 3 over 4. And you see what? X minus 1 right here, less than a quantity. And this what we call delta. Alright, now we kind of go backward. We're going to answer the question. Whenever you give me a number epsilon positive, epsilon could be 0.1, 0.001, 0.0001, doesn't matter how small or how precise your approximation for the limit is, you give it epsilon. I will let delta equal to 3 over 4 epsilon, okay? So if epsilon is 0.1, this is 3 over 4 times 0.1. This is 0.01, and this is 3 over 4 times 0.01. If that happens, then what? You gave me epsilon.